Okay, there are 4 equations you need to know for this small assessment on Monday. The first one, that pressure equals force divided by area. Okay, so hopefully you remember the force is measured in newtons and area is measured in meters squared, which will give you the pressure measured in pascals. Okay, so if it's newtons per meter squared, it's also pascals. Now you might find that the area is given in centimetres squared, in which case it would be newtons per centimetre squared, okay? But newtons per metre squared are measured in pascals. Now, when you're using this equation here, it might be given with, say, an object which might have different dimensions. So, for example, you might have an object which looks something like this, and they might have faces A, B, and C. So, for example, if this was 20 centimetres by, say, 10 centimetres, and then this might be 50 centimetres, and they might say, okay, its mass is 5 kilograms. So if its mass was 5 kilograms, and we took G to be 10, we would say that the weight of this would be 50 newtons. So say this weighed 50 newtons. That's the force it exerts on the ground. Now, depending upon which face it was on, would depend upon the pressure that it exerts on the ground. So obviously, the smallest face is face A, because A has the smallest cross-sectional area, all right? Whereas, obviously, B is a lot bigger, and C is a lot bigger because of this length. So if we were to look at A, so if all of this weight was focused on A, if it stood on face A, the cross-sectional area of A is 20 times 10. Now that would be measured in centimetres. That would be 200 centimetres squared. Okay? Now if we were doing pressure being force over area, we could say, well, pressure is force over area is 50 divided by 200, which is obviously 0.25 newtons per centimetre squared. So that's one way we could do it. But if we were to do it in pascals, we would do it in a different way because we'd convert our units, okay? Because it would be a factor of 10,000 times out, okay? So this, if we were to do it in meters squared, would be 0.2 times 0.1, which is 0.02 meters squared. So instead of being 50 divided by 200, it would be 50 divided by 0.02, okay? And this will give us an answer of 2,500 pascals, okay? So if we do that calculation, we'd have 50 divided by 0.02, which is 2,500 pascals. Now then, we could also have a question which looked something like this. This would be our second equation. Now our second equation is pressure difference measured in pascals is H rho G. Now this is height, density of the substance, and the acceleration due to gravity, or the force per unit kilogram, okay? Per kilogram. So the pressure difference, so for example, if we had, say, a pipe, and if the pipe contained a fluid, and that fluid was, say, there, I filled the pipe and it went all the way up to, say, there. Now if we had this part here, if they said, well, the top of this is atmospheric pressure. Now atmospheric pressure is 100,000 pascals, or 100 kilopascals. Now if they said the height difference between there and there was, say, 20 centimetres. Let's think about what's happening then. There's clearly a greater pressure here, which is pushing this liquid this way because there's a lower pressure here. So here we've got a higher pressure. Now that pressure difference between this pressure here And that pressure there is H, where H is the height, times rho, which is the density of the liquid, times G. Now, the density of the liquid, if we pick water, that would be 1,000 kilograms per metre cubed. So let's have a look. What must be the pressure difference between this region and this region here? So P is H rho G. H is 20 centimetres, which is 0.2 metres. The density of water is 1,000 kilograms per metre cubed. And G, of course, is 10. So this would be 0.2 times 1,000, so this would be 200, times 10, which would be 2,000 pascals different. So the difference in pressure between that and that is 2,000 pascals. Now if we look at it closely, we can see this pressure must be the greater of the two, because this one is forcing this fluid upwards. There's a greater force upwards, which is why it's raised. So this one must be 100,000 plus 2,000, which is 102,000 pascals. So that's an example of where you would use the pressure difference being H rho G. Height times density times G. Now, another equation you need to know is called Boyles Law. Now, Boyles Law states that P1 V1 equals P2 V2. So if we have particles contained in a container, in a box, if we increase the pressure, then the volume will be decreased, okay? So if we've got a box containing particles, if we were to halve the volume of that box, the pressure inside it would double, because there would be twice as many collisions on the surface inside the box. And of course, the pressure is caused by these collisions. So a typical question using Boyles Law would be something as simple as a gas canister. So they might say, there's a gas canister, and the gas canister has a volume of, say, 100 centimetres cubed. And we could say the pressure is, 500,000 pascals. So the pressure isn't enormous, it's 5 times atmosphere. And they could say, what would happen if the canister was opened? What would be the total volume that this gas would occupy at atmospheric pressure? Now, atmospheric pressure is 100,000 pascals. So we would say, okay, P1 V1 equals P2 V2. Pressure 1 is 500,000 times volume 1 equals pressure 2, which is going to be atmosphere, which is 100,000. That's times V2, which we don't know. So in order to work out V2, we'd say 500,000 times 100. Now we're multiplying on this side, so we'll divide both sides by 100,000. And that equals V2. So if we look here, we can get rid of 100,000. That means that V2 equals 500 centimetres cubed. So the volume that this gas would occupy if the pressure was reduced to 100,000 pascals, if the canister was opened, the total volume it would make up would be 500 centimetres cubed, which is obvious really, because the pressure was 5 times greater there. Therefore, when it's reduced by 5 times, the volume goes up by 5 times. Okay. Now, when you're using Boyles Law, I've used centimetre cubed. It could easily be metres cubed, but I didn't need to convert in that context. All right. Another law you need to know is the pressure law. Now, the pressure law, what's really important about the pressure law is that you use Kelvin, because obviously you remember Kelvin, 0 Kelvin is minus 273 degrees C. So when we're using the pressure law, we have to make sure we are using Kelvin. So for example, the pressure law states that P1 over T1 equals P2 over T2. Now again, this is using the same principle of, we've got the box containing particles, And all those particles are moving around randomly, in random motion, and they are colliding with the walls of the container, which gives it a pressure. Now, if you were to heat up this container, what would happen is you'd be giving the particles inside it more kinetic energy, so they'd be colliding with a greater velocity into the sides, and therefore a greater force. So we can see there's a relationship between pressure and temperature. Now, a typical question on this might look something like this. So in a container, we have a gas, and that gas might be at 20 degrees C. Now we're going to heat this gas up from 20 degrees C to another temperature. But first we need to know what's the pressure inside. So we'll pick atmosphere, so we'll say it's 100 kilopascals. Now we're going to heat it up to 200 degrees C. What will be the new pressure? Now the most common mistake in this question is thinking that this temperature here is 10 times greater than this one. It's not at all, because it's not in Kelvin, okay? If it were in Kelvin, we could do this and see if there's a proportionality, but whilst it's in degrees C, we can't see if it's this proportional relationship in the same way. So, if we consider we've got 20 degrees C, gas, air, atmospheric pressure 100,000 pascals, and we're going to heat it in its container to 200 degrees C, what will be the new pressure? All right? The first thing we would do is we'd convert 20 degrees C to Kelvin. So we'd add 273 degrees. So that would become 293 Kelvin. 200 degrees C added to 273 becomes 473 Kelvin. Now we can use the equation P1. Pressure 1 was 100,000. So when we put 100,000 here, remember, kilo means 1,000. 100,000 divided by temperature 1. The temperature 1 is 293. And that equals pressure 2, which we don't know, divided by 473. So the pressure now at this new temperature equals, the first thing I'll do is I'll say I need to times both sides by 473. So P2 equals 100,000 times 473 divided by 293. And that equals 100,000 times 473 divided by 293 equals 161,433 pascals. Okay? So we can see the new pressure is 161,000 pascals. After we do a question like that, we think, is it realistic? So this is roughly 300, this is roughly 500. Okay, so it's gone from 100,000 pascals to 160,000 pascals. Obviously this is not quite double, and that relationship seems the same. So therefore we look at our answer at the end and say, yes, that is realistic. Okay, and we remember, absolute zero is the temperature at which all particles stop vibrating. So you need Boyles Law, the pressure law, the pressure difference being H rho G, and you also need pressure is force over area. Okay, I hope that's useful.